Before we begin section 9.1, I want to remind you of something from chapter 3. It's been a long time. So right here in 3.1, at the very, very beginning of the course, we learned that there's a population mean, which is mu, and a sample mean, which is x bar. And down here we were talking about how mu and x bar will not be the same, but they should be close. Mu is the population average, x bar is the sample average. And of course, because of sampling error, no sample is ever perfect, but they should be close to each other as long as you took a random, unbiased sample. Now it is time to really have the rubber meet the road, so to speak, in regards to this phrase. What does that mean, should be close? That is what chapter 9 is all about. Chapter 9, we are going to determine what should means and what close means. And we do that with something called a confidence interval. So we're going to start off in section 9.1, which is going to be confidence intervals for a population proportion. So we start off with a point estimate. So a point estimate is a single statistic value that's used to estimate the value of a population parameter. Now you've seen those words before. Statistic is from a sample, something like x bar, your sample mean. And that should be close, hypothetically speaking, to mu being your population parameter. So we worked with that in chapter 3 quite a bit. And now we all want to expand that a little bit to talk about proportions. P hat is your sample proportion. We learned that in section 8.2. And that should be close to P, your population proportion, hypothetically speaking. Right. Remember that the ones with the bars on their heads, x bar and p hat, those are statistics. They're from a sample. And the Greek letter mu and this letter p are the population parameters. So suppose you want to know the true proportion of all red beans in a large box of red and white beans. You reach in with your scoop and you get 30 red beans and 90 white beans. So I have a picture here. If you click on, well, you can't click on it, but if you go to this bit.ly link, so go to a website. Let me pull my Chrome here. And then I actually have it right here, but I'll type it bit.ly.com/bean-box, right? Oops, hold on. There it is. It's bean-box. All right, bean-box, enter. And you press that and you're going to come up with this web page right here that has 3 pictures of this box of beans that is in my office right now. That's my office keyboard. That's what I'm using. And there it is. You can see the bean box and there's the little scoop, right? So you take a sample, and there's a little scoop of it. And in that scoop, there are 30 red beans and 90 white beans. You follow the logic? Now, just to keep in mind, you might be thinking to yourself, what in the world do I need to know about beans for? You don't. The bean box is a metaphor. This is a population. This is all the people. Say, all the voters in Michigan or something like that. And the red beans are representing people that have a certain characteristic. Say, all the voters in Michigan that, I don't know, want to make abortion illegal, or all the voters in Michigan that are going to vote for the Democratic candidate for governor, or all the voters in Michigan that are, going to vote for gun control. Pick something, right? So this is a metaphor for a larger thing, right? We don't really care about beans. I mean, it makes nice soup, but it's not what we're interested in. What we're interested in thinking about this is how this is a metaphor for a larger thing, which is taking a sample, the little scoop, from the population. Okay, and of course, how do you do the scoop? Well, you can do it a lot of different ways, but the most efficient way usually is to call people up. So you call them and say, hey, who are you going to vote for in the next election? Or, are you going to give away Halloween candy this year? Or, what do you think about the situation in this country, or et cetera, et cetera. So you'll ask people questions, and the red people are the people that are saying, what you're interested in, and the white people are the ones that are not interested in what you're interested in. Okay. All right, so with that, we have our box. Now, what parameter am I really trying to estimate here? Well, what I really want to know is the proportion of red beans in the box. Let's say this is the people that want to make abortion completely illegal. Right? So if that's the case, I want to know what proportion of people in the entire box would do that, would vote that way. So the box is everybody, and the red beans are the ones that are going to vote a particular way on a particular subject. So I'm interested in the population proportion, and the symbol for that is P. Okay, P for proportion. Now the total number of red beans in my sample, that's in my little scoop, is 30 and 90, which makes 120. So 120 is my scoop. There we go, I just made that boxed. Now, what is this total number of red beans in my box? Well, the red ones are the ones I'm particularly interested in, the ones that are going to vote for the Democrat in the next election or whatever, right? And that would be 30. There were 30 red beans right here, 30 red beans and 90 white beans. That means there were 30 red. That's what I'm interested in, okay? All right, so x equals 30. All right, now what's your best estimate? And this is getting at what we're talking about here, your single best estimate for the population parameter. So your best guess for the proportion of red beans in that box is p hat, which is x over n. You learned that formula in section 8.2. X was 30. There were 30 red beans in my scoop out of 120 beans total, which gives me a value of 0.25. All right, now, do I really think that it's like that? Do I really expect that the true proportion of red beans is 0.25? Well, no, not exactly, but I think it should be close, right? So, no, they will not be exactly the same, but p hat should be close to p, as long as we took a nice random sample and all that stuff, unbiased sample. As long as the sample was random and unbiased, etc. All those things from section 1.5 that we don't want to mess up. You don't want to ask biased questions. You don't want to ask loaded questions. You don't want to have an unfair interviewer, all that good stuff. Okay? So they should be close. They're never going to be exactly the same because, of course, it's a sample. So sample isn't going to be exactly like the population, but it should be close to it. And that's what we were getting at right here with this box, which we saw in section 3.1, which is that your population values are a constant. They are some unknown number. So for example, if I go back to my bean box, this box has a proportion of red beans. It just does, right? If I pulled them all out and counted every last one of them in my office, I could do that. The problem is that that would take so much time and money, right? So it exists, I just don't know what it is, right? But it's the proportion for the whole box. Whereas I could get my scoop, and that gives me my proportion for my sample. That's p hat. So p is the proportion for the whole box. P hat is the proportion for the sample. Let me type that up real quick. There we have it. So p is the proportion for the whole box. It's some constant unknown value. It just is, right? P hat varies from sample to sample. So if I take one scoop, that'll be different from another scoop. That'll be different from another scoop. Now, every scoop is a little bit different, but they all should be close, hypothetically speaking, to P. Okay? Now, how do they vary from sample to sample? That's what we learned in section 8.2, right? So in section 8.2, we learned, oh, it's the standard error and it varies in a certain way, has that formula, et cetera, et cetera. So that's what we're going to do in this chapter. We're going to use the sample statistics that we know to create ranges, i.e. intervals, for the unknown population parameters, because usually, in most cases, we don't know the whole population. We only know a sample. So we'll say, okay, I'm going to take that sample, I'm going to make a window of where I think the population proportion or population value will be located. So for example, we use p hat to make a window where we think p will be. Right? We're not 100% sure where p will be, but we think it'll be in this little range that we'll make for ourselves. That's the whole idea behind chapter 9. When you don't know the whole population, you take a sample and then you make kind of an interval of where you think your population parameter is going to fall. And that's it in a nutshell. Of course, it's more complicated than that, but that's the basic idea behind it all. So let's stop right there, and we'll pick back up in the next video with talking more about how to make those intervals and how it is constructed.